There are several types of things we need to consider when we talk about building a SAN architecture. The first thing we need to consider is high availability. And this usually means providing a dual fabric scenario so that we have two paths always to get to the storage. We need our path to be highly available, and we need to make sure that they don't drop any frame. We also need to plan for fault isolation. If we have an event in the fabric, we want to make sure that that event affects as small a number of hosts or storage arrays as possible. Oversubscription is also something that we deal with. It's not often that we have unlimited bandwidth, so we need to make sure that our oversubscription ratios are meeting what our vendors define for our different storage arrays. Security is also top of mind in a data center environment. It is also top of mind in a storage environment. We want to make sure that the right hosts are accessing the right resources. There are other scalability concerns, such as how many switches I have in my fabric. There are limits to the number of switches that I can have, so I need to make sure that I plan for that. Finally, I may also need to provide connectivity for my virtualized servers, and I need to plan for that as well. So when I'm looking at the major design factors for my SAN, the first thing I need to take a look at is port density. How many ports do I need today, and how many ports am I going to need over X number of years in my SAN fabric? I need to build a topology that can accommodate those port requirements. I also need to know what is required from my network as far as performance. If there's anything that I need to do in regards to traffic management, for instance, applying a quality of service level to a certain application, or letting a certain application use a faster path and a less critical application to use a slower path, I need to know that for my traffic management. We already talked about fault isolation, but we also need to talk about management, how we secure and possibly simplify management in our different designs. Earlier on in our lessons, we took a look at some of the different designs that are available. One of the traditional designs is a core edge design, where servers connect to the edge switches and storage connects to the core switches. The reason that the storage connects to the core switches is that the core switches are usually more robust, such as modular-based chassis that have higher availability, because we always want to have access to our storage no matter if I lose an edge switch. If a couple servers can't get to my data, that might not be as big of a deal as if all of my servers can't get to my data. I normally use less expensive edge switches to scale out to the number of servers that I need, and I use the more expensive core switches to provide the higher availability for my storage. I need to make sure that I've designed the links between the core and the edge switches in a way that maintains the fan-in ratio that my vendors recommend. I also, in this scenario, have two separate fabrics, a fabric A and a fabric B, in order to meet my high availability requirements. This model allows me scalable growth up to the core and can evolve very easily into an end-of-row or top-of-rack design. This is a traditional SAN design for growing SANs. From this design, I can very easily move into an core edge design. So we wanted that scalability at the edge for the servers previously. Now we want to use those same concepts and be able to scale out for our storage devices as well. So our core edge design can very easily migrate into an core edge design. Finally, depending upon your environment, you may have a collapsed core design where everything connects to two core switches. This can be great for a lower oversubscription ratio and allows you to have very fast access to your storage. If it's a smaller environment, it also provides room to grow. If you're using a modular-based chassis with 6 slots and you're only using 4 of the slots, you have 2 slots left to grow. You also don't waste any ports on inner switch links because you don't need any. Everything is connected to the same switch. Finally, This can be very easy to manage because I have single points of management versus multiple points of management from multiple devices. Once again, this is a very normal design for small SAN environments or high-performance SAN environments, and it achieves the high availability in the same manner that all the other designs have by having two separate SANs, a SAN A and a SAN B. In this case, there's only one device that makes that network up on each side. When we talk about oversubscription, we're usually talking about the fan-out ratio and sizing ports and links. The factors that are used in determining our oversubscription ratio are the speed of the host's interfaces, the speed of the array interfaces, and then the types of links in between those, as well as the types of servers and applications that are connected to those links. In the example below, I'm showing a 10-to-1 oversubscription ratio because I have 240 hosts or 240 gig of available bandwidth going into 24 gig of bandwidth at the storage array side. Storage vendors usually provide guidance in this process, and the ratios usually range between 4-to-1 and 20-to-1. Another item that we need to consider when we're designing a SAN is fault isolation. It's a very popular trend to try to consolidate your storage, and we have the ability to virtualize SANs in something we call a vSAN, very similar to a VLAN. That is a wonderful feature to use. A single fabric gives you increased storage utilization and reduces your administrative overhead. However, there are some drawbacks to it, and they need to be considered. If you were to take multiple SANs and move them onto a single fabric, your faults would no longer be isolated. There are technologies such as vSANs that enable consolidation and scalability while maintaining security and stability. But vSANs have constraints and fault impacts. Usually, a fault in a single vSAN does not affect other vSANs on the network. But if you were to physically lose a device that was carrying traffic for multiple vSANs can be affected. This is the same with any other virtualization technology. SAN design is very important because we need to provide a high-speed, lossless access to data. We need to use the SCSI protocol to access data in a very high-performance manner across the network, and we cannot drop frames. This is the foundation for all block-based access and storage connectivity for a storage area network. So it's very important to consider these design scenarios that we've talked about. Please spend some time getting to know them, and please join me for our next lesson, Understanding Storage Networking Services.